Welcome to Lab 3, where we are measuring the magnetic field of a bar magnet. The purpose of this lab is to use a bar magnet and a mobile device to measure the magnetic dipole of a bar magnet. Some important concepts include Biot-Savart's law and the distance-dependent formula. The main assumption for this lab is that the bar magnet acts as a dipole. In this lab, we measured the location of a magnometer and a mobile phone, then placed a bar magnet perpendicularly at the end of a meter stick. We then took the phone and the magnometer and we placed it horizontal to the center of the bar magnet. We then moved it horizontally closer to the bar magnet until we hit our desired value. Some observations that we made is that when the phone is far away from the magnet, it measures a near zero value for the magnetic field in the x direction. As it moves closer to the magnet, this x value increases. We also noticed that we had to place the phone precisely to avoid interference with the Earth's magnetic field and/or other objects in the area that projected a magnetic field. Calculations for this lab were fairly simple. Using the equation we got from the Excel file, we are able to get n, which is our slope, which is negative 1.9512. The y-intercept is our ln of k value, so we raise it e to that power to get our final k value of 4.22 times 10 to the negative 6. We then rearranged Biot-Savart's law to solve for u and get 2.211 a times m squared. We also wrote code to theoretically predict this value. At the beginning of our code, we define our one constant, which is u over 4 pi. We then create a magnet at the center of our graph at the origin, and then plug in 2.2108 as our magnitude of the magnetic moment, which we calculated in the slide before. We then created a function that calculates the magnetic dipole at a given distance using Biot-Savart's law, and then created arrows to represent the magnetic field at each of our distances. We then repeated this as we wanted to create multiple arrows. Off our code, we finished the last of the arrows and then calculated the magnetic field off axis at 45 degrees. Our result can be seen here. Our line of best fit was y equals negative 1.9512 x minus 12.329. Our average d perpendicular was 0.22 meters, and our b net average was 5.5 times 10 to the negative fifth. However, our theoretical calculations had it at 1.16 times 10 to the negative 5. Comparing our experimental to our theoretical results, we get an error of approximately 500%. Some sources of error include inaccurate location for the magnometer and improper calibration before each measurement, as well as other sources of magnetic fields within the area, such as wires or tables. What if we hadn't oriented the experiment to compensate for magnetic north and had instead laid out the meter stick at some intermediate angle with respect to Earth's magnetic field? How would the results have changed? Our results would have been skewed significantly, as the effects of the magnetic field from Earth would either add or subtract to our data, changing our numbers and giving us inaccurate results. What if we were to stick two identical magnets together end to end and run the experiment again? How would we expect the measurements to differ? Our measurements would be in the same direction with the same signs, but they would be doubled in magnitude. In conclusion, bar magnets can be modeled as magnetic dipoles, and the distance is directly related to the strength of the magnetic field.